So this is linear algebra, math 313. And you can mute yourselves, so it's easy to get. So math 313, linear algebra in the summer, it's very hard because we move at a fast pace. Because we need to do in 3.5 weeks what's normally done in 15 weeks during the regular semester. There's a lot of information that I posted on Blackboard. And if there are any questions before we start, please ask. So let me switch to a kind of whiteboard here. So to just remind you that you must go to Blackboard often, because that's where all the information is. In particular, you will have the course information and syllabus. You will have the assignments. And when you finish the assignments, you upload them to Blackboard. And you will have the text, which is in course materials. So I posted the first chapter, and there will be 4 or 5 chapters that we have to cover in the course, and they'll all be posted in course materials. And if I have to send an email, I do it via Blackboard, and the email goes to normally your Lehman email, whatever is there on Blackboard. That's the only way I have to communicate with you. Generally, we will have class meetings Monday to Thursday at 9 o'clock. Obviously, a lot of students can't come at 9 o'clock, but everything is recorded and uploaded to YouTube. And there will be 2 playlists on YouTube. First, there is linear algebra from last summer. So all the lectures for the course are posted there. And in addition, I will be having a separate playlist for what I talk about in these morning sessions over the next 4 weeks, and that's posted separately on YouTube. So those are available 24 hours a day. I'm also going to have help sessions. I know some people can't be here in the morning. So help sessions tentatively are Monday through Thursday at 7 o'clock p.m. on Zoom. So you log on at 7 and you're welcome to ask any questions about the material or to listen to whatever other questions other people may have. If no one logs on at 7, I log off, but I will try every day, every class day at 7 o'clock to be available on Zoom. And I would encourage you to take advantage of it. All right. Anything else? This is an asynchronous course, which means the exams are given, you take them at home and upload your answer sheet to Blackboard. You do need a way to convert homeworks and exams to PDF files and upload the PDF. But here, there's no expense of a textbook because the textbook is free, basically. I wrote it up. I wrote it up. Okay. If there are no questions, we will start. And linear algebra starts with linear equations, which is the subject of chapter 1. And you begin to learn about linear equations in high school. You solve equations like 2x equals minus 9. And so this is the equation. And you want to find the solution. Solution is x equals minus 9/2. This is an equation in one variable. You might have an equation in two variables. And this will have infinitely many solutions. Or an equation in three variables. So you need to be able to solve these equations and find all solutions. It doesn't matter what letters we use for the variables, x, y, z, u, v, w, r, s, t. Very often, especially for a linear equation in n variables, the general form is a1x1 plus a2x2 plus a3x3 up to an xn equals b. That's one linear equation. And the coefficients are these numbers a sub I. And in linear algebra, a number is called a scalar. So these words are synonymous. Number, scalar mean exactly the same thing. And numbers typically in linear algebra are either real numbers or complex numbers. So 7 and the square root of 19 are real numbers. 3 plus 2i is a complex number. And if you don't know complex numbers, I uploaded a material on complex numbers in course materials. Most of the time we'll deal with real numbers, but you shouldn't get to a 300 level math course without being familiar with complex numbers, and occasionally we'll use them as well. In this first chapter, I'm going to prove all the theorems for real numbers. That is, real numbers means these coefficients are real and you look for solutions that are real. But everything that I prove about equations with real numbers will be true for equations with complex numbers. And we often divide equations into two types. So in the first type, a1x1 up to an xn equals 0. If the left-hand side is 0, the equation is called homogeneous. And if you have a1x1 up to an xn equals b, which is a non-zero number, the equation is called inhomogeneous. We also say that a1x1 up to an xn equals b is a non-zero equation if one of the coefficients of the x's at least, if ai is different from 0 for some I. So the zero equation would be 0x1 plus 0x2 plus 0x3 equals b. That's the zero equation. That just means that all the coefficients of the x's are 0. Now, if b is different from 0, It says no solution of b is different from 0, because no matter what numbers you pick for x1 up to xn, the left-hand side will be 0, but the right-hand side is non-zero. And everything is a solution if b equals 0. Because if the coefficients are 0 and the right-hand side is 0, no matter what number you pick for the numbers you pick for the x's, you'll get 0 equals 0, which is correct. Okay, so this is all now basically vocabulary. You've all taken calculus, so you're familiar with sigma notation. That's the capital Greek letter sigma. If you have something that looks like summation use of I, say from I going from 4 to 7, this means U4 plus U5 plus U6 plus U7. Okay? Just summation. Sigma notation, which is just a symbol for summation. So you can also write the general equation as summation I goes from 1 to n, let's say j goes from 1 to n, aj xj equals b. So this notation is exactly the same as this. And this is just sigma notation for writing an equation. Okay. So there's a solution of the linear equation is a sequence of scalars numbers that solve the equation. I apologize if my writing is bad, but everything is written neatly, printed out in the notes, so you can always read this. And the notes are what you're supposed to study. And we write the solution as a column vector, what we call an n-dimensional column vector. So for example, one solution of the equation (4x plus 7y equals 0), or 4x1 plus 7x2 equals 0, these are the same equation, is you choose x equal to 7 and y equal minus 4, that's the solution of this equation. We write the solution as a column vector. And in fact, you might say the general solution, I mean, this is one solution. There are lots of other solutions. For example, you could take x equal to 1 and y equal to 3/7. Because if you let x equal 1 and y equal 3/7, you get 4 plus 3, sorry, equals 0. That's not right. 4 is minus 4/7. So 1 minus 4/7 is another solution of this equation. The general solution, well, if you solve for y, this is really just high school algebra. So this, I assume, you can do easily. 7y is minus 4x. Y is y over 4/7x. So for any solution, given x, this is y, and given any x and y that satisfy this equation, you have a solution. So the general solution as a vector is x and minus 4 over 7x. Okay. So that's the general solution of this equation. If you take the equation 4x plus 7y equal 5, and you're looking for the general solution, you can solve for y. 7y equals 5 minus 4x, or y equals 5 over 7 minus 4 over 7x. So as a vector, the general solution is for any x, y is 5 over 7 minus 4 over 7x. This is the general solution. This is the equation, and this is the general solution. Every solution is of this form. Now you could say, in this equation, I have x and y. I solve for y in terms of x, but I could also have solved for x in terms of y. I can say, well, in this equation, 4x equals 5 minus 7y, or x is 5/4 minus 7/4 y. So the general solution can also be written as, for any value of y, let x equal 5/4 minus 7/4 y. And you can say, well, how can it be that one equation has two different general solutions? Well, if you look at this, the set of all of these vectors for all values of x is exactly the same as the set of this vector, these vectors for all values of y. So you can write the general solution in different ways. They're both correct, just different ways of writing the same thing. It's no different from saying that 2/4 and 3/6 are the same, even though you're looking at different numbers, 2 and 4 and 3 and 6. So these are equal. And similarly, these are equal in the sense that this gives you the same set of solutions. Questions about that? Okay. So in 300 level math classes, we actually state and prove theorems. And the first theorem is very simple. It says that every non-zero linear equation, what does a non-zero linear equation look like? a1x1 plus a2x2, and then variables a n x n equals b. And non-zero means at least one of the coefficients ai is different from 0. Every non-zero linear equation has at least one solution. And why is that? Well, proof. The equation is nonlinear, means at least one of these coefficients is different from 0. So let's say a sub j naught is not 0 for some number j naught in the set of integers from 1 to n. And this is standard mathematical set theory notation. And under course materials, I also have a set of notes on sets. And if you're not familiar with this, you need to just look at the first few pages of that. So at least one of these coefficients is different from 0. So some here I have aj naught xj naught. So I can say aj naught xj naught, if I take everything and put it on the other side, is b minus, let me use sigma notation, summation aj xj. J goes from 1 to n, j not equal to j naught. And so I fix this, I bring everything else to the right-hand side of the equation, I get this. And because aj naught is different from 0, I can divide by it. So I can divide by aj naught. And what this says is, in any solution, x naught has to be this. Or I can choose any scalars for aj, j different from j naught. And once I pick the xj's, I define aj naught by this formula. Again, if my writing is bad, this is formula 3 on page 5 of the notes. So if we have at least 2 variables, you have infinitely many choices for the values of the xj's, and so you have infinitely many solutions of the equation. So this is slightly jazzed up, but it's not much more than high school algebra. So again, we write our solutions as n-dimensional column vectors. This is an n-dimensional. N-dimensional means you have n different numbers. Column is written as a column vectors. And we let Rn be the set of all n-dimensional column vectors. R1, just the numbers. It's a column vector, but just one number in it. You can think of that as the real line. R2 is what you used in all your math classes. It's all x1, x2, or you can write xy, but just all points in the plane. This is x1, x2. R3 is your usual three-dimensional space. If you wanted to write this as x, y, and z, you would think of this as the x-axis, the y-axis, and the z-axis. And you have points in space. But for R4 and dimension 4 or greater, there's no easy way to picture what they look like. But just because you can't draw a picture doesn't mean these are not concrete mathematical objects. So n-dimensional space, and the n-dimensional space Rn is exactly the set of all possible column vectors with n coordinates. Okay. And Rn, we will see, is the basic or the most important example of what is called a vector space, which is what we will be studying at length in the course. Now, there's an algebra of vectors, so we can define addition of vectors. You only define addition of vectors that are of the same dimension. You cannot add a two-dimensional vector and a three-dimensional vector. So suppose we have x. Let me just write it like this. I use boldface in the notes. x1, x2 up to xn. And y is y1, y2 down to y sub n. These are vectors in Rn. So you add these vectors component-wise. So in the sum of the two vectors, the first component is the sum of the first components of the individual vectors, as is the second and so forth, down to the nth. So for example, if you have x is 3, 6, minus 2, and y is 1, 5, 1, minus 1, 5, 9, x plus y, that's 3, 6, minus 2, plus minus 1, 5, 9. You add the components. 3 minus 1, 6 plus 5, minus 2 plus 9. You get 2, 11, and 7. Okay. So that is vector addition, no matter how many coordinates you have, no matter what the dimension is. And vector subtraction is defined by subtracting the coordinates. So in this example, when you subtract, when you do this minus this, you get 3 minus minus 1, 6 minus 5, minus 2 minus 9. That's 4, 1, minus 11. Okay. And we're not defining multiplication of vectors, but there is something called scalar multiplication. So if you have a scalar c and a vector x, you can define c times x. You can multiply a vector by a scalar. So let's say the vector is x1, x2, down to xn. You multiply a vector by a scalar by multiplying every coordinate by that scalar. cx1, cx2, down to cxn. So for example, if x is the vector 1 minus 4, 8, and c is the scalar 7, then 7 times x is 7 times 1 minus 4, 8. You multiply each coordinate by 7. 7 times 1 is 7. 7 times minus 4 is minus 28. 7 times 8 is 56. Right? And vector addition and scalar multiplication satisfy very nice algebraic properties. So vector addition properties. So if you're not familiar with the words I'm about to use, you're about to learn them and you will be familiar with them. So vector addition is associative. That says if you have vectors x, y, and z, if you take x plus y and add them, because vector addition is a binary operation. We're defining how to add two vectors. So you take three vectors, x, y, and z, you can add x plus y and then add z to that. Alternatively, you might have y plus z and add them, and then add x to that. So these could be different vectors, but vector addition satisfies what's called the associative property. So this vector equals this vector for all x, y, and z. That's what it means to say that vector addition is associative. It's also commutative. That means x plus y is always equal to y plus x. We also have what is called the zero vector. The zero vector is the vector with all coordinates equal to 0. And x plus 0 and 0 plus x is equal to x for all x. So the zero vector is what we would call an additive identity. It's just like the number 0 in arithmetic. 0 plus 3 is 3. That is, the scalar 0 plus the scalar 3 is 3. The vector 0 plus the vector x is the vector x. And we also have additive inverses. For all x, there is a vector x prime such that x plus x prime is the zero vector. And we write x prime as minus x. So, for example, if x is 3, 2, then x prime would be minus 3 minus 2, because in this case, x plus x prime is 3, 2 plus 3 minus 2, plus minus 3 minus 2 is 3 minus 3, 2 minus 2 is 0, 0, the zero vector. So every vector has an additive inverse. And scalar multiplication also has some nice properties. Scalar multiplication has some nice properties, namely, so for all scalars, C and C prime scalars, and vectors x and x prime, if you multiply the two scalars and then multiply the vector by C, C prime, that's the same as doing scalar multiplication, C prime x and then C times x. This is a kind of associative property. If you have C plus C prime times a vector x, that's Cx plus C prime x. And if you have C times x plus x prime, that's Cx plus Cx prime. And also, if you multiply any vector by the scalar 1, it doesn't change the vector. And you have to do as many exercises as you can with vectors to learn about them. Really. So you can think of Rn as the set of vectors. This is all n-dimensional vectors. And sitting inside of Rm, you might have a subset W and a subset W of Rn is called a subspace if it satisfies the following three properties. First, the zero vector belongs to W. Right? The zero vector is the vector with all coordinates equal to 0. Second, W is closed under vector addition. What this means is that if W is a vector in W and W prime is a vector in the set W, then the vector sum W plus W prime is in W. So if you have two vectors in W, W and W prime, their sum is in there. And the third property is that W is closed under scalar multiplication. So if C is any scalar, that means a real number for us, and W is any vector in W, then C times W is in the set capital W. So that's what a subspace is. Now, let's just look at an example. We're looking at R2, the plane. What is the x-axis? So let W, so x-axis is all the points with y equals 0. So if I let W be the set of all vectors x0 for any x in R, that's the x-axis. And I claim this is a subspace because, first of all, so W is all vectors where the second coordinate is 0. So in particular, the 0 vector is in W. And if x0 is in W and x prime 0 is in W, then the sum, when you add these two vectors, you get x plus x prime 0 plus 0. So the second coordinate is still 0, so it's in W. And C times x0 is cx c times 0. Any number times 0 is 0. So this is also in W. So if I take, for example, the x-axis in R2, that's an example of a vector subspace. Now, what is a fundamental fact in linear algebra? Well, there'll be several fundamental facts. Let's see. Sure. So the subset W of Rn is called closed under linear combinations. What does this mean? So if whenever you have vectors x1 up to x sub k in W and scalars You can take the vector x1 and multiply it by c1. You can take the vector x2 and multiply it by c2, and so forth, up to the vector xk, which you multiply by ck, and then you add up these k vectors. This is what's called a linear combination of the vectors x1 up to xk. So a linear combination of a finite set of vectors is the vector obtained by multiplying each vector by a scalar and adding up all the vectors. So we say that a subset is closed under linear combinations if whenever you pick any finite number of the vectors and take any finite number of scalars, this linear combination is in W. This symbol means in. Is in. And a simple lemma says that suppose we let V stands for vector space. If we take the vector space Rn, a subset W of V is a subspace if and only if, that's what this double-headed arrow means, if and only if W is non-empty, there's some vector in it, and W is closed under linear combinations. And there is a kind of dual result to this, which is theorem 2. We're looking at the notes. This is on page 12. The VBRN, that S be a non-empty subset of V, the set of all linear combinations of vectors in S is a subspace of V. And what does a subspace mean? A subspace is a subset of V that contains the zero vector and is closed under vector addition and scalar multiplication for this set W. Moreover, W is the smallest subset of V, subspace of V. That contains S. Okay. Now, the important thing in the study of linear equations is the following theorem. This is theorem 3. And this is really important, so I'll give it a star. The set W of solutions of the homogeneous linear equation A1x1 plus A2x2 and any number of variables a n x n equals 0. Homogeneous means that the right-hand side is 0. Is a subspace of Rn. So before I prove this theorem, this is really something that deserves to be proven, I want to look at an example. Suppose we have the homogeneous equation, and this is the example on page 13 of the notes. 3x1 minus 2x2 plus x3 equals 0. So this equation has many solutions. Here are a few solutions. 1 minus 1 minus 5. Why is this a solution? Let me see. So let's check. We let x1 equal 1, x2 equal minus 1, x3 equal minus 5. You get 3 times 1 minus 2 times minus 1 plus minus 5. This is 3 plus 2 minus 5. That's 0. So that checks. Let's look at another. 9, 8 minus 11. Let's check if this is a solution. 3 times 9 minus 2 times 8 plus minus 11 is 27 minus 16 minus 11, and that's 0. So that checks. 0, 3, 6. 3 times 0 minus 2 times 3 plus 6 is 0 minus 6 plus 6, that's 0. So that checks. So these 3 are solutions. Let's try to find the general solution. So from this equation, if I choose any numbers for x1 and x2, that determines what x3 has to be. If I solve this equation for x3 has to be equal to minus 3x1 plus 2x2. So the general solution, if I have x1, x2, x3, x1 can be anything, x2 can be anything. But once I pick x1 and x2, x3 has to be minus 3x1 plus 2x2. And if I want to express this in a very simple form, I have x1s and x2s here. If I separate out the part that involves x1, I have x1. Here I have no x1, and here I have minus 3x1. And then the parts that involve x2, 0, x2, 2x2. If you just check the rule for vector addition, this vector plus this vector equals this. And this vector, if I take the vector 1, 0, minus 3 and multiply by the scalar x1, and I take the vector 0, 1, 2 and multiply by the scalar x2, the general solution is any linear combination of these two particular vectors. So the general solution, W, let me just write it like this. W is the set of all vectors of the form for x1 and x2, any scalars, any numbers are. So this concrete example, I take this equation. What is the set of all solutions? What we call the solution space, or the kernel, or the null space. It's this set of all linear combinations of these two vectors. This is the subspace generated by the set S, consisting of the vectors 1, 0, minus 3, and 0, 1, 2. So for this homogeneous linear equation, the general solution, or the solution space, the set of all solutions, is this subspace generated by these two vectors. In particular, the solution space, which means the set of all solutions, is a subspace. In fact, it's a subspace generated by these two vectors. Again, it's very important to work through these examples extremely carefully, because this is the sort of thing I will ask you on an exam. I'll give you an equation and say, compute the solution space. Find the subspace of all solutions and find a set of vectors that generate the subspace. So that's theorem 3. And you state it and sketch the proof. And this is on pages 13 and 14. The set W of solutions of the homogeneous linear equation A1x1, A2x2 to AN xn equals 0 is a subspace of Rn. So we have to show three things: that the set W contains the zero vector, is closed under vector addition, and is closed under scalar multiplication. So first of all, if we let all the x's equal 0, a1 times 0, a2 times 0, and so forth, up to an times 0, it's just adding 0 to itself n times, and you get 0. So the zero vector, the vector with all coordinates equal to 0, is in W. That's the first property that had to be satisfied. Second, let x and y, these are these n-dimensional vectors, be in W. So that means that a1x1 plus a2x2 up to an xn is 0, and a1y1 plus a2y2 up to an yn is 0. And then add the equations. When you add, you get a1 x1 plus y1 plus a2 x2 plus y2 up to an xn plus yn is 0 plus 0, which is 0. Which means that the vector x1 plus y1, x2 plus y2, xn plus yn is in W. But this is just the sum of the vectors x and y. So W is closed under vector addition. And if I take this equation and multiply it by c, I get ca1x1 plus ca2x2 up to canxn, to c times 0, which is 0. Which means, but this is the same as a1 cx1, a2 cx2, an cxn equals 0. So the vector cx1, cx2 down to cxn, which is c times the vector x, is in W. So W is closed under scalar multiplication, and you prove the theorem. So when you have a homogeneous linear equation, the set of solutions is a subspace. Now that's for a homogeneous equation. What can we say about an inhomogeneous equation? Well, let's look at an example. Suppose we have 3x1 minus 2x2 plus x3 equals 6. And maybe you should spend a minute and check that the vectors 1 minus 1, 1, 9, 8 minus 5, and 0, 3, 12 are solutions. And find two more. So I'm just going to pause for a minute and give you a chance to do that. Let's see. So all you have to do to check these are solutions is to plug into the equation. So let's look at the first. If I take 3 times 1 minus 2 times minus 1 plus 1, that's 3 plus 2 plus 1 is 6. That checks. If I look at the second vector, 3 times 9 minus 2 times 8 plus minus 5, 27 minus 16 minus 5 is 27 minus 21 is 6. That checks. If I take 0, 3 times 0 minus 2 times 3 plus 12. That's 0 minus 6 plus 12, that's 6. That also checks. And it's easy to find more solutions. Suppose I say, I'll just pick up numbers at random. X1 equals 7, X2 equals minus 4. So then 3x1 minus 2 times minus 4 plus x3 is supposed to be 6. See, 3x1, that's 3 times 7, minus 2 times minus 4, that's 21 plus 8 plus x3 is 6, or 29 plus x3 is 6. So x3 has to equal minus 23. So 7 minus 4 minus 23 is the solution. For example. So there are lots of solutions. And suppose we want to find the general solution. So we have the equation 3x1 minus 2x2 plus x3 equals 6. So whenever we pick x1 and x2, if you solve for x3 is going to be 6 minus 3x1 plus 2x2. So the general solution will be x1, x2, x3. But x3 has to be 6 minus 3x1 plus 2x2. Let me write that in an interesting way. I have, first of all, 0, 0, 6 plus x1, 0 minus 3x1 plus 0, x2, 2x2. That's 0, 0, 6 plus x1 times the vector 1, 0 minus 3 plus x2 times the vector 0, 1, 2. So the general solution, or the solution set, you're looking at the set of all vectors 0, 0, 6 plus x1 times 1, 0 minus 3 plus x2 times 0, 1, 2, where x1 and x2 can be any real numbers. You could also write this as 0, 0, 6 plus w, where w is in the subspace capital W that we saw a few minutes ago when we were looking at the homogeneous equation, 3x1 minus 2x2 plus x3 equals 0. The solution space was all linear combinations of 1, 0, minus 3 and 0, 1, 2. Where capital W is the set of all linear combinations 1, 0, minus 3 plus 0, 1, 2. Or I could write this as I like, as 0, 0, 6 plus W. This is a certain subspace W, but translated by a certain fixed vector. So the solution of the inhomogeneous equation is not a subspace. It's a subspace translated by a vector. The subspace is the subspace of solutions of the homogeneous equation, and the vector is a particular solution of this equation. In fact, we look at 0, 0, 6, and we plug it into the equation, we get 3 times 0 minus 2 times 0 plus 6. 0 plus 6 is 6. So this is definitely a solution of the inhomogeneous equation. And a translate of a subspace is something we're going to call an affine subspace. So an affine subspace is a subspace that's shifted by a fixed vector. And in this example, the solution of this particular inhomogeneous equation is an affine subspace. And in general, that always happens. And that is the substance of our next theorem. So this is on page 16. Theorem 4. The set L of solutions of the non-zero linear equation a1x1 plus a2x2 up to an xn equals b is an affine subspace of Rn. Non-zero means at least one of these coefficients is zero. Every linear equation, every non-zero linear equation has a solution. Let the vector v be a solution of the equation. Now, associated with this inhomogeneous equation, we have the associated equation, homogeneous equation with b equals 0. So let W be the subspace of solutions of the associated homogeneous equation a1x1 plus a2x2 up to an xn equals 0. If W is in the subspace W, then a1x1 plus a2x2 up to an xn equals 0. V is a solution of the original inhomogeneous equation. So a1v1 plus a2v2 up to an vn is equal to b. Suppose I add these equations. I get a1 v1 plus x1 up to an vn plus xn is B plus 0, or B. So W plus V is a solution of the inhomogeneous equation. This is B plus W, same. W plus V, B plus W. So V plus the subspace W is contained in the solution space. You take any solution of the homogeneous equation and add it to a particular solution of the inhomogeneous equation, you get a solution of the inhomogeneous equation. And I claim conversely that every solution of the inhomogeneous equation is of this form. So how do we show that? So let's see, we let L be the solution space of the inhomogeneous equation. And we let W be the solution space of the homogeneous equation. And we let V be an L, and we just showed that V plus W is contained in L. If you take a particular solution of the inhomogeneous equation and add any solution of the homogeneous equation, you get another solution of the homogeneous equation. I want to show L is contained in V plus W. And if one set is contained in another, if set A is contained in B and set B is contained in A, the sets are equal. So that V prime, let's say it has coordinates V1 prime down to Vn prime, V and L. So A1 V1 prime plus A2 V2 prime up to An Vn prime equals B. And V was a solution also, A1 V1 plus A2 V2 up to An Vn also equals B. Now with these two equations, let's subtract them. When I subtract, I get A1 V1 prime minus V1 plus A2 V2 prime minus V2 up to An Vn prime minus Vn is B minus B is 0. So this vector is a solution of the homogeneous equation. So V prime minus V is in W. That is, V prime minus V is equal to some vector W in W, which means this solution V prime is of the form V plus W. It's in V plus the subspace W, which means the whole set of solutions of the inhomogeneous equation is contained in V plus W, which you already saw was contained in L, so they have to be equal. L equals V plus W. So that is a pretty proof of the result that the set of solutions of an inhomogeneous linear equation is an affine subspace. Okay. Now, I'm going to stop here because let me explain what we did today. We just covered sections 1 and 2 of the first chapter. And tomorrow, I will try to cover sections 3 and 4 of the first chapter. Now, as I said in the course information, in summer school, we have 14 classes plus the final. And in the academic year, there's 14 weeks of work plus the final. That means every day we cover a week's work of material from the regular semester. So that's what I just did, a whole week's work in the last hour and a half or so. And that's the pace we have to go through in order to cover the course. And that means that every day, every evening, you really need to spend a couple of hours studying the material and working problems. And you have to do basically every night what you would do in a week during the regular academic year. And there's no way to avoid that in a 4-week summer session. So I really encourage you to put in a lot of time every day and take advantage of the fact that I'm available at 7 o'clock every evening to answer questions. If no one shows up, I log off. But if people are showing up, I'll stay generally as long as it takes to answer questions. So these notes are on Blackboard, and I encourage you to download them and study them. Yeah, that's really good. Keep it. Okay. Any questions before we end for the morning? So I will post this on YouTube shortly, and I'll be back tomorrow, and I'll be around tonight at 7. Bye all.